Hello, everyone. I am Muhammad Ali Javidian, an assistant professor in computer science at Appalachian State University. Thank you for being here. Today, I will share how we turn the expectation maximization algorithm into a practical and provably convergent tool for domain adaptation in Gaussian DAGs when the target is missing. In short, this is about making transfer learning work when domains shift. To set the stage, let's start with a plain transfer learning under the usual IID assumption. In a standard transfer learning, we quietly assume the source and target are IID, independent draws from the same distribution. When this holds, a model trained on the source generalizes to the target, and life is good. Please look at the figure. In the left panel, source and target share the same probability distribution. So train on source and test on target works. On the other hand, in the right panel, the target has shifted. So the decision rule learned on the source no longer matches the target and performance drops. In short, plain transfer works in stable regimes, but fails under shift. So the question is, why does domain shift matter in practice? Here is a concrete story. A lab trains a 20-gene sepsis score on mice. It fits great and is well calibrated, so they deploy it as is to ICU patients. But humans differ. The cell type mix and assessment platforms change. That's a change in probability distribution of X. And some regulatory links change. Parts of P of Y given X shift. Please look at the figure. In the left panel, on most data, the learned boundary fits well, about 88% accuracy. On the other hand, in the right panel, on human data with covariate shift, the feature distribution moves. The same boundary cuts through the wrong region. The takeaway is, if we ignore domain shift, even a well-trained model can fail when moved to a new domain, and accuracy drops to about 64%. That means a large misclassified slice appears. To reason about reliable fixes, let's discuss some of the main shifts in causal models. Here are 3 common shift patterns in causal models. Please follow the figure. First, covariate shift. P of x changes while P of y given x stays the same. Second, target shift. The class prior P of y changes. Third, generalized target shift. P of y changes and parts of P of x given y change under constraints. We will use these structures to guide adaptation. However, these are not the only possible shifts, but we focus on these 3 because they cover many real cases and let us design principled identifiable updates. With that in mind, let me define our domain adaptation task precisely. In the source domain, everything is observed. In the target domain, the same DAG holds, but the target variable t is unobserved. Our goal is to impute t robustly under shift, assuming a linear Gaussian model and a known DAG. Before our method, a quick refresher, an EM algorithm and why it suits missing data. The main idea is simple but elegant. EM turns hard incomplete data maximum likelihood estimation into two alternating steps: expectations and maximization. In the E step, we fill in missing parts with their expected values under current parameters. In the M step, we maximize the expected complete data log likelihood. This alternation makes learning with missing data practical, and it monotonically increases the observed likelihood. Let me introduce EM notation. Theta represents model parameters to estimate, X represents observed data, and Z represents latent or missing variables. Now the question is, what happens if we run plain EM algorithm on the target domain starting from a random initialization to find unknown predictions? Here is a problem. If you run plain EM algorithm on the target domain with a random initialization, it will happily climb the observed likelihood, but it often settles in a bad local optimum because it's free to move all parameters. The fix is straightforward. Only adapt what can change across domains. We keep the invariant conditionals frozen from the source and only update the shifted blocks on the target data. This focuses learning where the mechanism changed and prevents the rest from drifting. What do we update in each shift scenario? In covariate shift, the feature distribution moves. We update the connections into T on the right strip so the mapping parents to T realigns with the new feature mix. In the target shift, we keep the connections fixed and update T's noise or uncertainty on the top strip to match the new variability. In another word, how much variation in T is not explained by its parents. In generalized target shift, we update both the connections into T and T's noise or uncertainty. Why this is good? Fewer parameters move means better stability, less overfitting, and it preserves EM's monotonic increase in observed likelihood while adapting exactly where the domain differs. With that idea, here is our first method at the population level. We define F sigma as filling the missing T for each sample using the current sigma. Then average across the target population. The target covariance sigma star is the fixed point of F, meaning sigma star equals to F of sigma star. Intuitively, fill in, then average, and repeat until nothing changes. Next, we make each iteration cheaper while keeping monotonicity. Here, the goal is speeding up EM by replacing the expensive GLS-M step with a single gradient ascent step on the updated covariance or parameter blocks, while still increasing the observed data likelihood in each iteration. This drops the per iteration cost from O of P cubed to O of P squared. And a small line search keeps the observed likelihood increasing. Now the practical recipe you can implement on a target data set. On target data, do the E-step on observed features, update only shifted blocks, reconstruct sigma by merging the updated blocks with the frozen parts, and repeat until convergence. Let me summarize the theory that guarantees this behaves well. Near the true target covariance, sigma star, the population EM update shrinks the error by a fixed fraction each step. Let's call that fraction kappa. If kappa is less than 1, the distance to sigma star gets smaller geometrically step by step. What sets kappa? It is gamma divided by lambda. Gamma means how sensitive the EM update is. More sensitivity leads to larger kappa. Lambda means how stable things are around sigma star. More stability leads to a smaller kappa. So a smaller gamma or larger lambda means faster convergence. Look at the figure. The points move inward across rings. Each ring is about kappa times the previous one. That's a contraction. The practical check is a spectral gap, a simple conservative test that tells us the largest eigenvalue of the non-target block of sigma star is smaller than the square of the smallest eigenvalue of the whole sigma star. If that holds, we are in the kappa less than 1 regime. That's the population story. What happens with finite sample? In finite sample scenario, with high probability, sample EM stays within a constant times delta divided by 1 minus kappa of sigma star. Here, delta captures sampling noise from source and target, and 1 over 1 minus kappa reflects the contraction amplifier. Let's see how this behaves on data in practice. We first test on a small structural equation model to validate the theory. As you can see in the table, the constraint EM adapts the right blocks and converges smoothly. Our first order EM adapts under both shifts. However, baseline Bayesian network fitted on the source and tested on the target data is okay under covariate shift, but fails under target shift. Unfortunately, in this scenario, Kiveri EM fails in both scenarios. Now let's talk about a large real network from plant genetics. We tested our proposed algorithm on a 64-node Gaussian Bayesian network in plant genetics. The domain adaptive EM improves imputation and downstream prediction compared to plane transfer and query EM. And finally, a classic single-cell signaling dataset. This dataset measures phosphorylated signaling proteins in human primary CD4 plus T cells under targeted perturbations. We treat anti-CD3/CD28 as the source domain and PMA as the target. Note that in the table, RMSE and MAE are reported in Z unit, not raw scales. What we see here? We see validation. Adapting only the shifted mechanisms give a strong gain for RAF, ERK, and PLCG, showing the method can leverage cross-condition data to improve prediction. Also, we see caution. For MEK and PKA, the gains are weaker, suggesting we need more robust extensions. For example, better handling of feedback, hidden variables, and non-Gaussian behavior. I mean possible misspecification. I will close with the limitations and scope of the current framework. In this framework, we assume linear Gaussian models and a known shared die. Also, closed-form global conditions are rare, and sufficient global convergence conditions are very conservative. Hidden confounding and misspecification can hurt. Let me end with the references and where to find the materials. Before I wrap up, two references that inspired this work. The Book of Causality by Yuda Pearl and Kivery's EM paper on covariance structures. I also want to thank the anonymous reviewers. Your comments really helped me sharpen the paper. All supplementary materials, code and data are on our GitHub. The QR code on the slide takes you there. If you try the code, I would love your feedback. I will be in Washington, D.C. during the conference. If this topic resonates with you, come say hi and let's chat. Thanks for listening.